In real life, okay, a practical application is if you want electronic ink to stick to a screen there we go, fun, okay? You need to put enough charge on that ink, there we go, so that it will be repelled by the electronic ink pixel matrix and stick to the screen. Too much charge, and it's going to get stuck to the screen and not come off. Not enough charge, and it won't stick. You see that? So in real life, it's a precise calculation. And here's the only tricky thing you have to realize. Charge comes in specific quantities. It comes in a package, an electron. It's 1.6 times 10 to the negative 19. It's kind of like when you go buy donuts at Dunkin' Donuts, right? You can either buy one donut, or half a dozen, or a baker's dozen. You get like 13, yeah. But you can't go, excuse me, can I buy like 8.5 donuts? They'll be like, no, that's weird, okay? So that's what we're gonna do. We're gonna just do a really quick, simple math problem here, okay? And I gotta make sure not to touch anybody's computer. Here's your sample problem, okay? I wanna get a piece of electric ink here. Here's a piece of ink to stick to the screen, okay? So what I'm gonna do is I'm gonna charge the ink up negative, and I'm going to charge the bottom plate of my Amazon Kindle or whatever positive. Or no, actually I don't want to charge it positive. If I want it to repel, I would charge it what? I would also charge it negative. Okay, it really doesn't matter. But here's what we're going to do. I'm going to pick a number nice and easy. Let's say we make, someone said 7, okay? I'm going to make the charge of my screen, Q, 7, okay? And then we'll just pick something really small. So sometimes there's a symbol called N. You guys ever see N? N is for nano. That's 7 nanocoulombs, okay? This N is for nano. Nano means 10 to the negative, anybody know? Ninth. It means billionth, okay? So you might have heard the term nanotechnology in the news a lot. And that's because we're trying to build things on the nanoscale, billionth of a meter. Computer chips are designed on the nanoscale. Eventually, the idea is if you can make little tiny, robots, you can inject them into your body to clean out your arteries or whatever. That's nanotechnology's basic idea. Okay? So the question is, let's say to get the ink to stick to the screen, we found out through whatever engineering that the Amazon Kindle needs 7 nanocoulombs of charge, 7 billionths of a coulomb. The question is, how many electrons would that take? Okay? This looks all complicated. We could use an equation, but we don't really have to. It's not that bad. How about this? How many donuts are in 3 dozen? If it's just a normal, not a baker's dozen. Baker dozen, you get 13. That's that bonus. It's just 36. That's the way you think of it, except it's not donuts. It's coulombs of charge, and it's electrons, okay? So the equation looks like this, okay? The amount of charge Q is equal to N times the number of electrons, okay? C is for coulombs of charge. It's getting used to this, okay? So in other words, in 7 nanocoulombs, there's a certain number times the charge of an electron. There's a certain number of electrons we need to get, okay, 7 nanocoulombs. That's what that means, okay? Actually, this should be number of electrons is what we're looking for. So the charge of a single electron, 1 electron is 1.6 times 10 to the negative 19th coulombs, okay? So this looks all mathy, but all it is it's like we want 7 dozen donuts, but 1 donut has this kind of charge. Think of it that way, okay? So in other words, let's just do the math. It'll make more sense once we do the math. We're going to plug in here, okay? 7 nanocoulombs means 7 times 10 to the negative 9th coulombs of charge is equal to a certain number of electrons we need times the charge of 1 electron. Or in other words, this is a lot of math to just say, if you want to know how many donuts are in a dozen donuts, okay, or how many donuts you have and however many dozens you have, you take the total number of donuts that you have and you divide it by the charge of a single donut. Think of it that way, okay? So in other words, if I take 7 times 10 to the negative 9th, that's the amount of charge I want, and I divide it by the charge of 1 electron, okay? This looks all complicated. That tells me N, the number of electrons, is what I'm finding, okay? N is the number of electrons. So there was an equation in the chapter that it looked all complicated, Q equals NE. And I actually really don't like to use that equation. I just like to use common sense more, okay? But some people found that helpful. So let's go and get out our calculators now and plug. If I take the amount of charge that I want 7 nanocoulombs, 7 times 10 to the negative 9th coulombs of charge, and I want to know how many electrons it takes to do that, I just divide it by the charge of a single electron. So in other words, if I had 3 dozen donuts, I would divide by 12. But in this case, we're not talking dozens of donuts. We're talking about nanocoulombs of charge, okay? So you divide by 12 to get number of donuts by the dozen, we're dividing by the fundamental charge of an electron, 1.6 times 10 to the negative 19. And we get, is that a small number or a huge number? 4.375 times 10 to the 10th. Yeah, it's a huge number, okay? 4.375 10 to the 10th, okay? So you can just write this as 4.375 E10 electrons, or that's the same thing as 4.375 times 10 to the 10th electrons, okay? 10 to the 9th is billions, so this is 43.75 billion electrons, okay? So in other words, if you want to know how many electrons it takes to charge up an object, you just have to divide it by the charge of a single electron, 1.6 times 10 to the negative 19th coulombs. It's such a small number, it's almost meaningless to most people. And that's why Dr. Robert Millikan in the 1930s won the Nobel Prize at the University of Chicago for figuring out how to measure the charge of a single electron there. Okay?